In this talk, we're going to continue the process of solving special types of recurrence relations. In particular, we're going to continue solving recurrence relations of order 2, so our nth term depends only on our n minus first and n minus second term, and we're only interested in the simplest type where you have constant coefficient linear recurrence relations. Now, we've already seen that when we have a recurrence relation of this sort, where you're given the first two terms, a0 and a1, and you're told this recurrence relation, a sub n is c1 a n minus 1 plus c2 a sub n minus 2, which is valid for all n greater than or equal to 2, we can write down this characteristic equation, r squared equals c1r plus c2. That's a quadratic equation. Often it has two distinct roots, and if it does, say alpha and beta, we know that the sequence alpha to the n satisfies the recurrence relation. The sequence beta to the n will satisfy the recurrence relation. That's exactly how we chose this characteristic equation, to force that to be true. And any linear combination, a times alpha to the n plus b times beta to the n, will also satisfy the recurrence relation. Then, in order to make sure that the first two terms are correct, we have to solve this system of two linear equations in two unknowns. Here, when n equals 0, we have a0 for our term, and when we plug in n equals 0 here, we get a plus b. When n equals 1, we have a1 is alpha a plus beta b. When we solve this system, we make sure that our sequence of the form a times alpha to the n plus b times beta to the n will actually match the first two terms and solve the recurrence relation. Because our sequence is uniquely determined by this recurrence relation, once we're given the first two terms, and we found a formula for a sequence which does that, we know that this must be exactly the correct sequence, and thus actually exactly the unique correct solution. And so what we've really shown is when the characteristic equation has two distinct roots, there is a unique solution, and here it is. But what if the characteristic equation, this quadratic equation, we could also write that as r squared minus c1r minus c2 equals 0, what if that has only one repeated root? Well, if it has only one repeated root, you could write this as r minus alpha squared equals 0. And of course, we know already from the quadratic formula, you could tell what alpha has to be. Alpha must be exactly c1 over 2, and it would be then true that, of course, alpha would equal, alpha squared would equal c1 alpha plus c2. So when there's one unique root, these equations must be satisfied. It is still true that the sequence alpha to the n satisfies the recurrence relations. That recurrence relation, again, is a sub n is c1 a n minus 1 plus c2 a n minus 2. But it's not enough to have just one sequence satisfying the recurrence relation, because not only, it's not just that that sequence will satisfy it, but also any multiple of that, in other words, a times alpha to the n, will also satisfy the recurrence relation. But in general, just picking the correct value for a will not allow us to match the first two terms correctly. Remember, we need a0, the first term, the n equals 0 term, a times alpha to the 0, to be a0, and the first term, a times alpha equals a1, and if a0 and a1 aren't chosen exactly correctly, this will be impossible. You might get lucky and it works, but in general, it's not possible because we have only one degree of freedom here, and we have to match the first two terms. So just as in the other case, what we really need is some way to have two independent parameters to mess around with in order to match the first two terms, which means we need another independent solution, meaning another independent sequence that satisfies our recurrence relation. And so here's my claim. In this special case, when the characteristic equation has a single repeated root, then the sequence n alpha to the n, alpha, remember, is our root, c1 over 2. This sequence also satisfies the recurrence relation. Why is that true? Well, let's just check by plugging it in. Here's our recurrence relation. A sub n is n alpha to the n. We're asking if that satisfies things. Is that equal to c1 times, now we have the n minus first term, so that would be n minus 1 alpha to the n minus 1 plus c sub 2 times n minus 2 times alpha to the n minus 2. Well, if we divide by alpha to the n minus 2, we get n alpha squared is c1 n alpha, and then I'm separating this out, distributing here the n minus 1, we'll have a minus c1 alpha plus c2 n, and we've divided by the alpha to the n minus 2, so we just have c2 n minus 2 c2. And let's see, here we go. Just correcting something earlier, I'm sorry, let's just continue here. I'm getting myself a little confused. Why will this be true? Well, alpha was the solution to the characteristic equation. So we know that n alpha squared is actually equal to c1 n alpha. I'm sorry, n alpha squared is actually equal to c1 n alpha plus c2 n. That's just the equation that says alpha squared is c1 alpha plus c2 all multiplied by n. So we know that this term on the left is equal to the sum of these two terms. So this whole equation will be true exactly when 0 equals c1 alpha minus 2 c2. Just correcting this real quickly, we have a minus, we want 0 to equal minus c1 alpha minus 2 c2, and we ask, is this necessarily true when alpha is a repeated root of the characteristic polynomial here, the characteristic equation? And the answer will be yes. How can we see that? Well, if we go up here, when we write r minus alpha squared equals 0, alpha will have to be c1 over 2 in order for that to be the same as this equation. And when we expand this, the constant term here will be alpha squared, and that will have to be minus c2. So I'll write that in here. Alpha squared must be minus c2. In other words, c2 has to be minus alpha squared, and minus alpha squared is minus c1 squared over 4. This equation that has to be satisfied is equivalent to 0 equals c1 alpha plus 2c2, and c1 alpha is equal to c1 squared over 2. 2c2 is twice this quantity here, which is minus c1 squared over 2, and we see that this equation certainly is holds. C1 alpha plus 2c2 holds. And what did we show with all of this algebra? We showed that this sequence, n alpha to the n, must also be a sequence which satisfies the recurrence relation. What does that tell us? That tells us that any linear combination of the sequence alpha to the n and n alpha to the n also satisfies the recurrence. In other words, our solution is of the form a sub n is some constant times alpha to the n plus some other constant times n alpha to the n. And using a solution of this form, we have these two parameters, so we can always have a solution to, when n equals 0, we need a naught equals a times alpha to the 0 plus b times 0 alpha to the 0, and a1, the n equals 1 term, must be a solution to this when n equals 1. That would be alpha a plus when n equals 1, you would get alpha b. So if we solve these for a and b, which is always possible, you just plug in a equals capital A equals A naught. Put that in here and you can solve for B. That's as long as alpha is not 0, which it won't be, as long as not both of these constants are 0. Then we get our solution uniquely. Let's see some examples of this. For the first example of a recurrence relation of this form, let's look at this recurrence where we're going to have a sub n equals 6 a sub n minus 1 minus 9 a sub n minus 2. Now with that recurrence we can start it however we want, so let's say that we choose to start it a naught equals 0 and a1 equals 1. Let's just see how our recurrence goes. We start with term 0, 1 for a naught and a1. Using this recurrence relation, the next term is 6 times 1 minus 9 times 0, so we have 6. The term after that is 6 times 6 minus 9 times 1, so we get 27. That's for a3. The next term is 6 times 27 minus 9 times 6. You can compute that easily yourself. 6 times 27 is 162 minus 9 times 6, which is 54, and we get 108. And it keeps going on and on and on like that. Can we solve this recurrence to get a formula for this sequence? Remember, here's a naught, a1, a2, a3, a4, etc. The answer is yes. The characteristic equation is just r squared equals 6r minus 9, or r squared minus 6r plus 9 equals 0, which can be factored as r minus 3, quantity squared equals 0. So alpha equals 3, this is the only solution. And what does that tell us? It tells us we can find the solution to this recurrence by solving the system of equations where 0, the n equals 0 term, is equal to a. Why do I have a? I should write this clearly. I want a solution of the form a sub n is a times 3 to the n plus b times n 3 to the n. So when n equals 0, I plug that in here for a naught is 0, and a times 3 to the 0 is a, plus b times 0 times 3 to the 0 is 0, and a1 is 1, and that will have to equal 3a plus 3b. Now this is a very simple system of equations to solve, since the a's are already given as 0, and then immediately you get 1 equals 3b. So a equals 0 and b equals 1/3 is the solution. And immediately we get that a sub n is just 0 times 3 to the n plus 1/3 times n times 3 to the n. That would just be n times 3 to the n minus 1. And we can check our solution with the first few terms. This is certainly 0 times 3 to the negative 1. This is 1 times 3 to the 0. This is 2 times 3 to the first power. This is 3 times 3 squared. This is 4 times 3 cubed. That's 4 times 27. And you can compute more and see that this formula for a sub n will give you every term of the sequence following along with that recurrence relation. Let's look at another example, which might seem a bit strange. Let's say we have the recurrence relation a sub n equals 2a sub n minus 1 minus a sub n minus 2. And before we look at an example with the initial terms, we can see immediately that the characteristic equation is just r squared equals 2r minus 1, or r squared minus 2r plus 1 equals 0. That's immediately seen to be r minus 1 squared equals 0. Alpha equals 1 is the only solution. So our solutions will all be of the form a sub n equals capital A times 1 to the n plus capital B times n times 1 to the n. Now, of course, 1 to the n is 1, so we just have solutions of the form a plus bn. So if you have this recurrence relation, solutions will always be of the form a sub n is a plus bn, linear functions of n, or you'll see that in a different language means that the sequences involved will be arithmetic sequences. Let's say we start with a naught equals 1 and say a1 equals 2. Well, if the sequence starts 1, 2, just using this rule, we'd get the next term is twice the 2 minus the 1, which is 3. The next term is twice the 3 minus the 2, which is 4. The next term is twice the 4 minus 3, which is 5, etc. And you can see immediately that this is just the sequence of natural numbers itself. What would that mean? That would mean if we wanted to solve 1 equals a plus b times 0, which is just a, and 2 equals a plus b, we would get a equals 1 here, and b equals 1. And so the sequence a sub n is just 1 plus n, and that gives us here a naught, a1, a2, etc. Very simple sequence because of this very simple recurrence relation that has only the single root. What if there are no real roots to the characteristic equation? We've already looked at the cases where there are 2 distinct real roots and where there's 1 repeated root. Well, if there are no real roots, then there are just 2 complex roots, and those will be complex conjugates of each other. So then there are 2 necessarily distinct complex conjugate roots. And I'll tell you what happens, though I don't want to go through examples here since not everybody is probably familiar with the algebra of using complex numbers. If you are familiar with complex numbers, I claim you do exactly the same thing we did in the case of 2 real roots. You can write the general solution as a sub n is some constant times one root, say alpha to the nth power, plus another constant b times the other root, which will be alpha bar, the complex conjugate of alpha, to the nth power. And you can solve for the constants a and b exactly the way we did before, only here we'll have complex numbers floating around in our solutions. And we get a formula for the nth term of our sequence. If our sequence starts with real numbers, and our coefficients c1 and c2 are real numbers, which was necessary in order to have the complex conjugate roots, we're starting with, say, real recurrence relations, then I claim, even though we'll have complex numbers that appear in the formulas, in the end, every term of our sequence will in fact be real, and it'll give you the exact terms that solve the recurrence relation. Again, if you're familiar with complex numbers, try writing down some examples. It'll be a lot of fun.